All right, so it can be section 6.4 work. So in order to do this, we have to some applications based on integration, and a lot of these are going to be done in physics. So if you take physics, you may see these again. And if you don't, these are at least some understand where these actually these are applied from. So one thing we're going to learn is about the force. So the force on an object exerts and when it moves. In this section, we're going to learn how integrals are used in physics, and it will be fully a physics topic, so don't worry, we're going to go full crazy on it, but it's a brief introduction of how they were used and that kind of stuff. So the first equation is going to use is one of the famous ones we know is force equals m times a, or in other words, mass times acceleration of an object. Okay, so that's how much force is behind this portion. So you can think of it like a punch. So how much force are you hitting somebody or hitting an object? Depends on the mass you have and the acceleration of your hand when it comes to it. So that's what that represents. The second, the work of an object is the amount of force an object does throughout the distance it covers. Okay, so how much work does it take to you to swing and to move yourself to actually hit something, right? That's what it means by work. Okay, so when it comes to the work, our equation is W equals F times D, where D is the distance the object travels. Okay? So if we do this into in a graph, again, let's say we have this portion where this curve represents the force itself at any given moment, let's say from A to B. Right? So this is the amount of force you like to, for example, you throw a punch at, right? So there's a way you go fast and you slowly accelerate based on how fast you go by. So this is going to be represented as our function in terms of the force itself. Okay, and we want to figure out how much work is being done throughout this punch you're throwing. So again, just like everything else, we want to find the work. Well, that's kind of finding the area underneath the curve. Well, again, using rectangles, we have the delta x, right? The change of x from one value to the other value. Okay, so that represents the distance, right? That represents distance from here to here throughout this entire curve itself. So what that means is we can rewrite our equation to be W equal F times D into now a generalized function. Where instead of F now we have the function of x in terms of the force of this object or punching itself times the distance, or in this case delta x, or the change of x. Okay. Well, again, right, we want to find the total amount of work. So that's just the work at one particular value. So therefore, the total work is going to be equal to the sum of all these individuals put together. Okay. Well, again, going to correspond to that, well, we know from our fundamental theorem, that represents an integral. So this represents the work of an object. So the work done in moving an object is equal to the integral of the function of the force function times dx, or again, right, the change of x is the same thing as the x, right, the thickness, right, or delta x itself. Okay? And this is what the equation we're going to be using for work an object does throughout this lifespan, through a distance. So you can see how this is going to be applied in physics or in our applications. So it says when a particle is located a distance of y feet from the origin, the force the object exerts is x to the third plus 2x pounds. How much work is being done when it is moving from x equals 1 to x equals 4? Okay, so again, going back to our equation. So this is our equation for work. It's going to be the integral and going from where to where, to the distance-wise, so from 1 to 4 of our function, so the force function. So we have a force of this dx. Now you're wondering, okay, well, when does this come into play? This is just extra information. This is just telling you it's located a certain amount of feet from the origin, and we're starting there. So in this case, we started from, let's say, 1 when it comes to it. So it's actually a little trick question, just throwing you off and seeing if you actually understand the concept itself. We actually don't even use that y feet from the origin itself when it comes to it. Okay, so we just integrate normally. So this is going to be x to the fourth over 4 plus x squared, evaluated at 4 and 1. So we just simplify right, playing the calculator. So 4 to the fourth power divided by 4 gives you 64, plus 4 squared is 16, minus, plug in 1, we just get 1/4, and then plug in 1, we get 1 there. Okay. So adding and subtracting the 1/4, or in this case the 5/4 itself, gives us approximately this. Pounds times feet, right? Because our force is given F times D, so it's going to be, in this case, the pounds times the distance, right? So in this case, it was feet. And there we go. That's how we're going to calculate work of an object. Okay. The next major concept when it comes to physics, and you guys can get into it, is it's a very cool one. It's about strings, stretching and compressing strings, and the most famous one of them is called Hooke's law. And again, once you guys get into physics, you know Hooke's law is a huge portion of physics. Believe it or not, it's compressing. So if you guys go to the gym, and if you compress it and decompress your muscles, right, it's all done in this type of format. So that was the main focus on how to do this kind of stuff. So again, next type of physics problem we're going to call is we're compressing a string or stretching it out. Okay. Hence, Hooke's law states that the force required to stretch or compress a string is directly proportional to x, meaning the function itself is equal to k times x, where k is the spring constant and f of x is the force function itself. So f is still the same as what we did above. It's still the force function itself. Okay. So again, way back, right, directly proportional. That means there's some value k that's going to be a constant throughout the portion or throughout the interval of itself. Okay. So again, breaking it down, so the equation for the amount of work needs to be done to be either stretch or compress a string is equal to the integral from a to b of kx dx. Okay. And the most amount of work we're going to be dealing with when it comes to springs is finding the k value itself. Because if you know, plug it in, you know, taking the integral of just x is just, it's pretty straightforward. It's just x squared over 2, right? But the k value is what we care about the most. And I'll give you guys a hint here. So the first thing we need to do is find the constant k and then integrate the function. But, now this is a huge but here. But the first thing we have to do is we need to make sure the distance is always in meters. That's a key thing. Okay. So going to be hints. In most cases, it will not be, and we have to convert it to meters itself. So they'll probably give you inches, feet, centimeters, and you have to convert it. So hence the example we're about to see right now. Okay. So example 2 says a force of 50 Newton is required to hold a spring that has a natural length of 10 centimeters to 13 centimeters. How much work is done in stretching the spring from 13 to 17? So notice, these are all in centimeters, right? So the first thing we're going to do is convert stuff like that into meters. Okay. So if you're not sure, right, centimeters, meters is a conversion of just dividing by basically 100. Okay. So if you go from 10 centimeters to meters, you just divide by 100, which gives you 0.1 meters. Okay, so there's a quick little conversion there when it comes to it. Okay. So we know that y is equal to k times x, right, because it's directly proportional according to Hooke's law. And we want to find k. So we know if it's 50 newtons, so that's the force itself, right, that's our function of f. So at 50 newtons, what is the k value itself? Well, it tells you if we go from 10 up to 13. So that difference between 10 and 13 is 3, right? So in that case, it's going to be 0.03 to be our difference between the kx values. That's how much it is stretched by. So solving for k here, meaning just divide it over, we get K is equal to approximately that. Now, if you're wondering why we do this, is we always want to see how much from natural strength, meaning that's basically 0, right? It's stretched from 0 up to how much? That's why we do subtract it from the 13. So if it was naturally, let's say 5, we would do 13 minus 5, and that would be the difference there. Here. So a key thing where it says from natural strength, so it's just, it's automatically at rest is 10 centimeters, but if you stretch it to 13, then it's not at rest, right? It's going to stretch out when it comes to it. So that's why we do that. So if we compress it, it's going to be the same thing. You subtract them to get the compression portion. Okay. All right, so now that we have K, now we can solve for W, right? The amount of work we actually need to deal with it. So the work is going to be the integral from here to here. So the distance between this portion and that portion. So we know it's going to be 0.03 up to 0.07. That's the distance between here to here. Right, again, always going back to its natural state. So difference between 10 to 13 and 10 to 17 gives you that. Again, always looking at the natural state. Cannot emphasize that as much. Okay. So from there, from K times X, we'll just integrate that. So not too bad, right? So this is going to be 16 x squared over 2, evaluated at those two values. Okay. So plugging it in for here, plugging that in, you get approximately this. And that's in joules. You don't have to know what the joules is, but approximately 3.33. That's the amount of work it is to stretch a spring from 13 to 17 centimeters. And there we go. That is 6.4.